Right, not being sure of your level of understanding, let's go right back to the very basics. Suppose we have a value. Let's consider the situation where we have the value of, let's change the colour, 3. Alright, so that's the one we're going to be playing around with, and I want to modify that or change it. I want to multiply it by 2. Now this is a process, and this process is applied to a value which, if we so choose, we can change to whatever we want. So this in fact here is our input, 3. So we put 3 into this process, and we have as a result an output. And that is our answer. We take that, we double it, and we get the output of 6. Number machines. Now basically this is an equation. Suppose we want to represent that as being able to be anything we want. Well, we put a letter in, X. And then we have our process that we apply to that value. And we have our number machine, and as before we have our output 6, and we have our input here, which I will call X, some unknown value. We put it in here, we apply a process of 2, and we get the answer of 6. Now this is our Y value, it's the output. And this is the input here, the X, right? It's a number machine, basically. If you get onto further maths, they're called, this part here is the function. This is the answer. So all it is a number machine. Now we're going to be taking a look at that shortly. Now let's consider this again. Our input, suppose we have a number line, and that is our input, and I'm going to start at a convenience 0, and it can be anything we want. Now up here our input was 3, 1, 2, 3. Now suppose that's a number line. Let's draw another number line here, and it can go on as that one can, and we go 1, 2, 3, 4, 5, 6, 7. So that is our 6 there. Now our number machine links this number here, our number 3, to the number 6, and we can show there's a connection by drawing a line. The two values are connected by that line. This line represents the consequence of applying that process, that number machine, that function, right? So it changes this value here into that, and that is our answer. The line just represents the change. It shows where that change is to, and it is there. These are two number lines. Now we don't have to do number lines horizontally. We can have, for example, well no, it's quite common. We can have our, hang on, control. We can have our input line, right, that's the input number line, that way, and we can have our output number line that way. That's all they are, is just number lines. We have changed the way they are in relationship to each other. This case, they're both horizontal. In this case, that one's horizontal, that one's vertical. So we still need to connect our 3. There's our 3. Let's pretend that the 6 is there, shall we? Let's pretend our 6 is there. Now, instead of going from there to there, direct line, alright, instead of direct line, what we do is we go up, and we go across. That point there represents a turn in the connection. And that's all a graph is. It has lots of turns where this number line is related to that number line. Right? So we've got that. This is the case where, to write the function, we have y equals the unknown value, and we multiply it by 2. That's all it is. It is the connection between the two number lines, and to show the relationship we do a single point. So this single point here connects that value on the number line there, the input, to that value there on the output. That's all a straight line graph is. Let's take a closer look at our friend here, the question. There's 2 conditions here, but let's look at the state where we have y is equal to, oh, by the way, they don't write it, but there's one of x. There's only one of them, one of that value. So if x is 6, there's one of them, plus the 2. Now that gives us, if we put in a single value there, we only get a single value there. That's what this does here. But this here is a slightly different thing. Right? But first of all, let's take a look at this situation here. And yeah, I'll leave the 1 in place. Let's pull up a graph package. Now we have here, let's put the equation in, hang on. Y is equal to some unknown value, and we add, where's the 2? Now let's just ignore the 2 for the moment. Y is equal to x. Here we go. Now look, that is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. They're just number lines. This represents, because it's a solid line, every single possible value on that number there, and every single possible on that number line, and every single value possible on that number line there. We if we want to plot it up, we go this line up here, cross to there, and we can see that value of y, the answer 2, is the consequence of putting the value of 2 into the function or the number machine, right? Now if we change, let's just put that on, there you go, that's the graph of y is equal to x. But, look, we have plus 2. So, in fact, we have here, let me just minimize that. Suppose we have y is equal to x, which is what we were just looking at. The left-hand side must have exactly the same value as the right-hand side. I'll call that y1. So if we have here 2, we must have 2 on the other side. Suppose we add 2 there. That must mean that we have y1, that value, plus 2 on there. What you do to the right, you have to do to the left, otherwise it is not equal. The value on this side has to exactly match the value on that side. So what this amounts to here, we got y1 and we shift it upwards by 2. Got that value and we move it upwards by 2. Let's have a look at the graph. Move this back up again. Y is equal to x. Now if I add 2 to that, we expect this line here to go up by the count of 2. So that point there will go 1, 2. That point there will go 1, 2. And that will be true of every single point on that line. So let's show that. We'll draw that one. We'll change it. We're going to put a 2 in there. Right, so here we go. Let's put in the other equation. Now this is a different value. Y is equal to x plus 2. And that's going to be a red line there. And here we go. That there is the original one. We have added 2. So you can see that it has shifted up. Every single point has gone up 2, 2. If we go up here, 2. It doesn't matter. Where we go on the blue line, it goes up 2. We've increased it by 2. Now this type of thing where you have an equals gives usually, not always, single values. The y would have just one value and it is dependent upon that. In this case, definitely, that y has a single value because that x has a single value there. That's because we have the equal sign. Let me clear those away. Delete. Thank you. Did I? Wait a minute. What happened? Bear with me. I need to get rid of that. I need to get rid of that. We don't have a single an equal sign. We have this. Let's take it a step at a time. Alright, now I'll just clear this lot away. Suppose, just for a moment, we have y and that sign. We haven't got the horizontal bit, just that sign there. X plus 2. We know what happens if that's an equals. This is not an equals. Now just think, we have a line there. That gap is much greater than that gap there. In fact, that gap there isn't one. So this side, if you were to measure gaps, that gap is much less than that gap. That's what this means here. The value of y will be less than whatever we get here. That's what it means. Less than. This here is less than whatever that is. So if we put a 3 in there for the x plus 2, we know that that is 5. So the value of y has got to be less than 5. If it's less than 5, it can't equal 5. Alright? It can't equal 5, but it can have all the values, every single value that exists that is less than 5. If I put that there, that's saying less than or equal to 5. So it would include 5. So it would be all the possible values that exist from and including 5 downwards on the graph. So if you have a graph here, alright, that's not very good, is it? No. if we have a graph here, let's draw the line. There are your axes. Doesn't matter where this crosses the vertical axis, the y, and there's your x. If it is less than whatever this value is here, we end up with what we draw is, can I do that? We make this a dotted line. It's just a convention, okay? It's just a way of showing it. What it means, if we have, in fact, this is a graph of y is equal to x. Look, that's y equals x. When you have a solid line, it's y is equal to x. If you have, instead of that equal sign there, if you have less than x, you have a dotted line. It's all the values, every value of y that is less than x. Suppose we have a point here on the line. All your y's are down there, and it goes on forever and ever. So we could include that value there, we could include that value there, we could include that value there. Goes up, but we cannot include that value there, because that value there be much less than this result here. How is this shown? Let's use my graph package and I'll show you what I mean. Hang on a minute, let's yeah. Let's pull that up again. Here we go. Now look, we have y is equal to x as the first thing. Alright, there we go. There's our y is equal to x. Whatever value of x we have, 4, go across, our y will be 4. That's y is equal to x. Now we put the plus 2 with the x, so we end up with y equals x plus 2, which would be the red line. There we are. There's our y is equal to x plus 2. So all the y's that would be less than, if we would have that point there, would be all the y values down here, down here, down here. You know, look, go across there, all those y values. All those y values are true for that point if it's less than or equal to. Alright, now look, let me just get rid of this, shall we? And get rid of that one. We now have that. And let's make it red. Let's make that red, shall we? So that one there we want to be red so it matches. There you go. Y is equal to x is that. Now what happens if we change it to y is less than? And let me find it on the keyboard. Where are you? Got it. Oh, come on, come on. That's not quite the equation that you've got in the question, but look what happens. See, it's a dotted line. Let me put that there. All the values of y that are less than that, so they are below the line, but not including the line. Notice it's dotted because it's less than. So if that is 6, the whole thing will be 8. Y cannot be 8, but it has to be less than 8. If x is 2 plus 2 gives us 4. So in the case where x is 2, y is all the values less than 4. Okay, so look, we have a line here. Suppose x is 2. How do I do that? Hang on. Okay, I think I've figured it out. Now look, suppose we use the value of x and we make it, what should we do, 3? Yeah, let's make it 3. I'll show you what I mean here. Now, we said x is equal to 3. We're going to set x at 3. But the range, you know, if it is 3, 3 there plus 2 makes 5. So I'm going to give it the range of 5 to, oh, I want it to go way down. Let's go minus 89. That doesn't matter. Don't worry about the value 89. Alright, so I just want it to produce this line here. X is 3, we said. So if x is 3, put 2 with it, you get 5. So look, if we come across here, that's 5. But we said it's less than. So it's all the values of y that are less than 5. So anywhere on that line there is our answer. But it has to exclude the actual point where x is 3. In other words, it has to exclude the value of 5 on the y-axis. Now if you do that for every single point on this line, you end up with a shaded area underneath. Let me just get rid of, shall I do that? No, I'll keep that there. Now look what happens when I do equals. This now becomes a solid line, and it's all the values of y that are below that line there. So if we put x is equal to 1, it's all the values of y from there all the way down to negative infinity. It goes on forever and ever and ever, downwards, all the time down, all the values of y. So that's what this equation is doing. It is stating all the values of y, every single possible value of y that is less than x plus 2. So it is the shaded area. The shaded area represents all the possible values of y.